people discover about it. And so for this large low shear velocity provinces, low shear velocity provinces. It is one of the most heated topic in the Earth interior, particularly for Earth's interior structure nowadays. As you can see from the topic, it starts from the observation of seismology. So what the people found at the time, that was quite a while ago. So probably in the 1980s, people at Caltech, like Don Hamburger, those group of people, they find that there's some wiggles from some seismic waves that are reflected from the Earth's core boundary. So considering this is my naive interpretation of seismology as a petrologist, so because there's a contrasting difference of density between core and mantle, and I interpret the travel of seismic waves in the Earth's mantle, similar like they transmit of light in the water or in the air. Okay, or the transmit of sound, let's say sound because it propagates through a certain medium. Okay, so when you hit a boundary, then you reflect. However, if your boundary is not exactly like this, and if there is some second order difference, as I draw here, and then you could, and then it's likely that you might see some reflection. Okay, I'm just doing some very naive, simple examples. Okay. So what this means is that there are some strange wiggles that people see in the seismographs. And then at that time, people in Caltech, not only in Caltech, but a lot of people in Caltech did make a great contribution to that. Was I say, okay, there might be something that is abnormal near the Earth's core boundary. And then people did more work because like petrologists, seismologists, they looked for different regions of the Earth's lower mantle in different parts. And then they found one beneath Africa and another one beneath the Pacific that has this relatively low shear velocity. So what the people found is that these two piles, I'm not drawing that very well. So they comprise their total mass is about approximately 5% of the volume of Earth's mantle that has this large low shear velocity. And it is just low shear velocity. Also seismology would explain that is due to its higher temperature, because the higher temperature you go, so it changes the shear modulus. So think about it. You have you have a rock, then you increase temperature, of course it becomes softer, and it's easier for you to shear the rock or something. So basically increasing temperature could decrease the acid shear velocity, but that is not the end of observation. So people then find that the bulk sound velocity has its anti-correlation with the acid velocity. So that causes a problem because high temperature calls for lower acid velocity, but also decrease the density, because at high temperature, it basically expand with the same mass, then you have lower density. So this causes a problem, and not only, and later on, actually people conserved it from another perspective, because for seismology, you did only get the seismic wave results rather than the absolute chemical density. It was at 2017 Nature work by Howard Lau, who is currently at UC Berkeley. Now the whole work looking at dividing the mantle into several layers. And then they look at the Earth's surface deformation. Then they use the GPS data in the recent 20 years. And their work shows that the bottom of Earth's mantle has slightly higher chemical density. So you know, through the Haber-Lous tidal wave methods, what they call the tidal tomography, basically is independent. So their method is temperature dependent to show that we have slightly higher density. So this causes something that's very interesting because if you only think about temperature, that doesn't work. Then people begin to think about something else, like composition. So when people map about it, look at the composition, easy way to think about is that, okay, you could have higher concentration of iron, okay? So to achieve this, a group of people represented by Lagros, 7 Nature work. What they did was that they did the mantle convection and the mantle crystallization in the magma ocean, and they found that the bottom layer of the magma ocean could be FeO rich. Actually, this could propose something that is really interesting, and to say that a certain kind of acidic magma that is slightly higher FeO rich then has a higher density. So basically, because you are exchanging FeO with that of magnesium, and FeO is much higher than magnesium oxide. So we can take it simple in this way. And of course, like I said, people, including me, that later on proposed that people could use the metals, like I said, equivalent to sulfide compositions to replace that. But some of the key ideas are similar, is that there could be chemical difference to change its density at the large low shear velocity provinces. So these are what the petrologists do, what the people consider the composition difference. But not only that, through the geodynamics, people looking at the mantle convection, and people do the simulation to show that when the mantle convection hits the boundary of the large low shear velocity provinces, it causes the turbulence and causes instability of the LSVPs. And therefore, this creates mantle plume. I'm not drawing very well. And this mantle plume hit the surface basically is what the people trying to explain with the kimberlite eruption, as well as oceanic island basalts. And in order to further match this two, geochemists analyzed the various noble gases. First, the helium-3, helium-4 ratio, etc., was very extreme isotope like tungsten hafnium isotopes that are expected from Earth's command boundary, but has been kept relatively long from the mantle convection. So you should find some place with a higher density to preserve these primordial geochemical components. So people propose large low shear velocity provinces is one of those. But this is not the end of it. There are still many things that people do not know about the large low shear velocity provinces. Is that although we call them large low shear velocity provinces, what people generally would know is that, okay, geodynamics have done work like more than 20 years ago, like Alan McNamara, etc. And they found that these two piles, they could not be too dense. So for example, if their density is more than 2% higher than the average of the mantle, ambient mantle, their calculation shows that the LLSVPs will collapse. So they cannot stay this high as this, what people call their thermal piles. And they cannot be too slow, too small. So if the density is less than 0.5 weight per for example. I don't know the exact number, maybe 0.3, let's say. And then this pile, they are not going to be a pile. They are going to mix with the rest of the mantle for mantle convection. So this is what the geodynamics constraint to show that with a reasonable density increase, these two piles are going to survive. However, there are a lot of things that still not clear nowadays. And from the seismology perspective, I think that what is not clear is that the exact location of the large low shear velocity provinces are not clear. People know one is beneath Africa, the other one is beneath Pacific, but people do not know exactly the location of them. I mean, different people's models give very different results. So their locations are not exactly the same. And also in recent years, work like Baba Romanowski from UC Berkeley, their global model shows that the LSVPs might not be just one piece. It might be composed of several pieces. And what the seismic wave that get actually is, to a certain extent, like an average. That depends on the model people use. And people think that it's likely that LSVPs are heavier at the bottom, and then the same density at the upper part of LSVPs, because LSVPs is defined by seismologists, seismological observation with a certain method. Okay, so the exact location of LSVPs are not clear in detail, and the density distribution of LSVPs are not clear in detail. And why the two LSVPs have a different height, people still have debate about it. But I do have to remind you that subduction is a process that people do. I would say half of the geophysicists still think that subducted slabs are the reason for the accumulation of LSVPs, because people also done the geodynamic work to show that subducted slabs could accumulate at the Earth's core boundary, but they could also have slightly density than the rest of the mantle, and then they piled up to form two piles. And so it's still debate. People don't know that the contribution of both to explain why it looks like that. And for geochemists, people still need to develop new systems or analyze more OIBs as well as kimberlite, because for samples that have been analyzed, I don't think the number is large enough to include or exclude some of the hypotheses. So it's still very dynamic field. And so in this paper that Natasha is going to lead will tell us that how does how does this subducted slab shape the topography? Is that how high or how low of the LSVPs by Professor Mingming Li's group? Okay, so I'm going to stop share my screen, and I would like Natasha to take over for the rest of the discussion. Okay, let's see. Me. That's it. Okay, Natasha, go ahead. Natasha, yeah, go ahead. I could not hear you. Now it's better. Could you speak a little bit more?
1, 2, 3,
Oh, yeah,
1, 2, 3.
Yeah. No, that's good. That's good. So go ahead.
Okay, well, I give it an additional volume just in case. So let's start. This paper is called Instability of the African Large Low Shear Wave Velocity Province due to its low intrinsic density. And this paper became extremely popular in the last few months Here you can see some of the headlines of popular journals, and there are even some speculations of an alien planet hiding in the center of the Earth. It was really interesting to read that one. The authors are Quan Yuan and Minmin Li. They are currently research assistant and assistant professor at Arizona State University. The history of Minmin Li: he did his bachelor's at Yunnan University, his master's at Institute of Geology and Geophysics, Chinese Academy of Science, his PhD at Arizona State University. He holds his postdoc research at University of Colorado Boulder, and currently he is in Arizona State University. For Quan Yuan, I didn't find a lot of information. I know that he was a researcher at State Key Laboratory of Geological Processes and Mineral Resources at China University of Geoscience. And he is now a PhD candidate under Minmin Li and Richard Herwig in the School of Earth and Space Explorations of Arizona State University. And he received a postdoc opportunity research at the California Institute of Technology. So let's start about the paper. The morphology of the large low shear velocity provinces has been investigated through seismic observations, and seismic waveform modeling studies have suggested that the African large low shear velocity province reaches a height of 1,300 to 1,500 kilometers above the core mantle boundary. And this value for the Pacific one is 500 to 800 kilometers. However, the results of seismic forward waveform modeling can contain trade-offs between the size of structures and their seismic velocities. So to estimate the height of those provinces more precisely, the authors calculated 17 global shear wave tomography models. And for each model, they calculated the lateral average DVS and the height above the core mantle boundary in vertical cross section. It is found that the lower mantle DVS has a negative decline most negative near the core mantle boundary, and then increases with height until a turning point like this, for example, where it changes from mostly positive to 0 or negative. The increase in the DVS can be caused by having a wider base in here of this province and then making it to the top at a larger height. So this turning point, as they interpreted, is marking transition from depths to depths without those provinces and represent the maximum height of these provinces, which is
yeah, we cannot see your screen changing, like the first screen has frozen. So
wait a second. I will. Can you see it now?
Yes.
Okay. So what I was talking about, the turning point, it may mark the transition from depths with a large low shear velocity zone to the zone without this province. And here it is for the top of the Pacific province at this point, which are red lines, and the top of African province, which is the blue lines. The second, I think my computer. Can you see another page?
No, it's the same, like the last one.
Jesus. Wait a second then. Tak. Can you see it now? The different slide?
Yes, now I.
Okay, then I will read like that. So the authors examined 33 vertical cross sections through those large low shear velocity provinces and found out the approximate heights with more precision. So it's with their approach, the maximum heights were 700 to 8,000 for the Pacific zone and 1,600 to 1,800 for the African province, which is pretty consistent with this regional waveform modeling. To account the difference of DVS magnitude in different tomography models, authors decided to normalize the DVS of each vertical cross-section in each tomography model by the maximum magnitude of the DVS in the cross-section before calculating those profiles. And here you can see that DVS absolute values, the green dotted lines, and the normalized values, the blue lines. And we can see that they pretty much coincide. So the zones where you can reach this zero gradient and the zones where the turning point for DVS happens. The question remains is what causes the large height difference between those two large low shear velocity provinces? And it has been hypothesized to be caused by compositionally distinct materials that are intrinsically denser than the surrounding mantle. Or also there can be other explanations such as purely thermal structures and clusters of slow anomalies, but it's still unknown. And previous numerical modeling and laboratory experiments have shown that the height of thermochemical pile is greatly controlled by its density and viscosity compared to that of the surrounding mantle. So probably it's more about the composition of these piles. And it remains unclear what mechanisms these properties control, through what mechanisms these properties control the height of a pile, and how to explain this great difference between the height of two provinces. And here the authors perform geodynamic modeling experiments to quantify the relationship between the height of piles and the density and viscosity of structures in mantle. So in these pictures, we can see that shortly after initial condition, the materials are pushed to form this thermochemical pile. And first, the authors decided to examine how initial volume of pile material can affect the height of this pile. They vary the initial pile volume from 3% to 11%. Well, here it is 4, but they actually took the minimum as 3, to 11%. And they show that the volume of pile material doesn't have a significant effect on the height of it. So it increases in lateral, but it doesn't increases in height if we add more material. They decided to take those numbers because if we take the initial volume less than 3%, the pile is quickly entrained into the mantle convection. And if we take the initial volume more than 11%, a global layer of pile materials formed near the core mantle boundary, which is not exactly the thing we can see through the seismic observations. We see two distinct pile zones and not one large. Next, they investigated the effect of buoyancy number B on the pile height. They found out that when B is smaller than 0.45, the pile materials becomes unstable and are mixed into the background mantle. And when B is larger than 1.25, the pile material forms a stable global layer, which is, again, not exactly the thing we can see. So here there are 3 snapshots presented with different Bs, and we can see how it affects on the height of pile material So the pile height decreases substantially when the buoyancy number increases. Next, they investigated the influence of background mantle viscosity on the height of the pile and found out that the height of the pile increases when the viscosity of mantle increases. Here you can see it pictured on this graph, and we can see that the effect becomes weak when the viscosity of the surrounding mantle is larger than 10 to 23 Pascal a second. They also decided to see how the viscosity of pile material influences its height. And they found out that there is only a moderate increase in pile height in here happens, but it happens only when the pile viscosity is at least hundreds of times higher than the background mantle. Next, they show the pile height for different combinations of pile buoyancy and viscosity of the mantle. They did 450 individual models for those two parameters. Here you can see the buoyancy and background mantle viscosity, and here is the height imaged in this color graph. We can see that the height of the Pacific large low shear velocity province can be explained by a wide range of those two parameters, those pink dots. And the African province can be explained only by a narrow range of buoyancy, and in which background mantle viscosity is unrealistically high, as the authors explain. And this is why the African a large low shear velocity province is defined as unstable. The results that shown above demonstrate that height of a stable thermochemical pile is much more controlled by the background mantle viscosity and the buoyancy number of the pile material. And those results are consistent with previous studies. Next, the authors decided to add some complexities to the model, and it is shown that adding more complexities such as spin transition in the lower mantle or compositional dependence of compressibility would affect the pile height, but only in small amounts. Like here we can see when the aspect ratio, which was taken in the previous slides, have these blue dots, and orange ones are for the aspect ratio of 6. They didn't quite explain it in details. What does it mean, the aspect ratio itself? But they only were talking about that it's more about the complexity of the model. So we can see that it doesn't really affect largely. So those effects on piles heights are minor. And it was found that piles can oscillate between phases, like phases of rising, phases of collapsing. And this is why those two heights of different large low shear velocities provinces may have those different heights. So if they're in different phases of oscillation, maybe this is why they have those different heights. However, in experiments provided in literature not connected with this research, the pile materials were covering more than half of the depth of a tank, and those continuous global layer always covers the bottom of the tank during the oscillatory process. So it is not exactly what we are seeing from seismic images, and this still can be discussed. And to summarize, the larger height of the African large low shear velocity provinces indicates that at least African large low shear velocity province is probably unstable. And vast height difference implies that the two provinces may have different densities and thus different compositions. The compositional difference between those two provinces can be suggested on the basis of different studies of radiogenic isotopes on plume-induced basalts above those provinces, which show that African large low shear velocity province is enriched by less dense subducted upper continental materials, and no such feature for the Pacific province. This is what the author concluded, that probably the compositional differences are the ones the difference in composition and dynamics causes those two large differences in sizes. That's it. Thank you.
Okay, I will drop that. Okay, okay, yeah, it's pretty good. Yeah, in
I
earlier,
only wanted to ask about this aspect ratio. If you probably read this article, maybe you know what specifically is it about, because after reading, I still have not clarified this for myself.
my interpretation for that is that what the geodynamics sees that you see how wide and how high they are. So my interpretation for this is that, okay, there are here they want to argue that the viscosity of the background mantle and the LSVPs basically is how hard the LSVPs compared with the ambient mantle, or how weak. So my interpretation is that it's really hard. Then through the mantle convection, then it could be shape within a certain place. Let me think about it, how to make this analogy make it work. Because the higher the aspect ratio, then I think that's it. Is it longer? It is, or thinner or longer? Thinner or longer? I think it's longer. So basically, it's like a rectangular, and aspect ratio 1 is a square. So I think my interpretation is that, okay, so how hard or how soft of the LSVPs determines how they are being squeezed into the final shape, which in this paper, they particularly point out the aspect ratio, which is something that I don't think people talk too much before, because people normally only talk about it, I say this, the volume, the total volume ratio of the LSVPs. So I think that's a key part of the paper is that they argue how hard of the LSVPs decides on the shape of the LSVPs. So which I think that's one of the, probably the one with the highlight in this paper about, which is also the one that in my introduction of this paper I didn't talk about, or when I summarize previous people's work, people didn't not talk too much about it. It's about how weak and how strong of the LSVPs, and also people began to look at the anisotropy at the LSVPs, and people did find there's the like Murray Long's group at Yale University a couple of years ago when I saw their talk, and they mentioned about that at the edges of this LSVPs, there is a stronger anisotropy, which they claim that is the deformation due to mantle convection or slab on the edges of LSVPs that causes to deform. So, but that one is mainly on the edges of this part. But this one they really want to say was this general weakness or strength of the LSVPs. I hope that answers your question.
Yeah. So does anyone else have any question? Yeah, the paper is not really that hard to understand, so I think there are not much questions about it.
So I could jump out to answer Ben's question.
I've seen that, yes.
Yeah, people don't know how old this LSVP is. Some people like me or some geochemists are trying to say that LSVPs are really, really old because only LSVPs are very old and is dense, and it doesn't mix with metal convection. That could make it the ideal reservoir for those primordial geochemical signatures. So that's and also the dense part normally goes to the core Earth core boundary. So this is one aspect. People think, possibly think that LSVP is formed at the end of magma ocean crystallization. Basically, that's its beginning in Haidian, quite a while ago. Well, so some other people, especially seismologists, and prefer to see it from another perspective, is accumulated by subducted slabs. So by that, you need to consider that how many slabs could locate the Earth's core boundary and pile them up, accumulate them together, because even every slab we see subducted won't all go to the lower mantle, because that was well being shown for the earlier work, like say Van der Heest at MIT, for example. His work in the late 1990s shows that some of the slab only going through certain angles that can travel through the mantle transition zone going to lower mantle. And some slabs doesn't reach the lower mantle, they stay at the transition zone. So if you consider that, then you do the mass balance calculation and considering how what's the mass volume of subducted slabs that subduct every year. Then I didn't follow the details for that, but my guess would be that at least the Phanerozoic, throughout the Phanerozoic, or the recent 1 billion year. So it's required. So it's not something very, very new for LSVPs. I mean, they could have new parts of the slabs, but all its components has a reasonable time. So I'm ranging from the lowest estimate to highest ones, that from 1 billion to 4 billion years.
In this paper, the authors only one time mentioned approximate age. They are saying that probably the African large low shear velocity province is enriched by subducted continent material, which happens during Pangea supercontinent cycle, and no such thing for Pacific, but it's the only time when they're talking about the age. So yeah.
I think Wumi, I think this is just open question. I don't know, because to me it seems people are trying to merge with two aspects together. So some part of it is from the early Earth, where you can also add some subducted slabs and mix them together. So I think it is just, so my own interpretation, I don't know what other people could think about it. My own interpretation is that it is really out of any constraints. So yeah, if you think there's a subduction, then you could say, okay, it should after the tectonic started. I would say yes. Yeah, I remember that it was almost 2 years ago. Luke Delsett, I think we did have his recording in our webinar list. So he compared the I think the mantle samples from the above the LSVPs, above African as well as the Pacific LSVPs, and then basically he did the plots to show that there's actually, I forgot the first 3 features that stand out from each other from 3 LSVPs. So one looks like have more subduct components that are more juvenile. yeah, that looks that's where I think Mingming also cited like that. I was trying to say, because in my interpretation that nowadays people not only see these two LSVPs, but people see more details. So people see these two are different, not only in height, in the aspect ratio, likely different viscosity, and those two have different compositions, likely, and also seismologists also observe they might form from different parts. I forgot details from the Barbara Ramoski's publication a couple years ago. So that one LSVP might be composed of 4 pieces, the other one maybe 2. Now, I don't know exact numbers, but the 2 of them could also have very different physical distribution. I didn't specifically say what type of physical distribution, property distributions are. Could be viscosity, could be density, could be velocity, and it's not a bulk. I mean, this density for 2 of them are not uniformly distributed, homogeneously distributed. So at least I think that's what the people have been found in the recent years, like in recent, let's say 3-5 years, and people still trying to discover more and more in more detail, with more details. Okay. So anything interesting, Natasha? Do you have any pictures, images in your computer you'd like to share with us? Maybe some pictures you took a long time ago.
Oh, I don't know. I don't have anything prepared. There are nothing interesting happening right now. So
Okay, that's okay. No worry. Also, Chuhin, is there anything on your computer you can share with us? I remember that I saw your picture. Maybe you can share with everybody about your trip somewhere, your field work before, and Malawi. Okay, that's okay. Okay, anyone to share anything interesting?
about the question from chat, it is pretty much okay. After the Omicron, there are not so many information about death or something like that. It's pretty much, I think, not going away, but everyone just forgot about it. So we don't have any restrictions now, and there are information in the internet that it's going on like pretty easy. So people don't have pneumonia, they don't have any extra difficulties with it. So yeah, it's like our government says, even COVID left Russia. It's like a joke after McDonald's, Zara, fashion brands and stuff like that left Russia. So they are telling us that even COVID left Russia. So now it's a pretty calm period.
Yeah, well, at least that's a good thing that people could walk around now. Okay, I think that's so much for today. And thanks, Natasha, for leading the paper reading. I think we could wait for the speaker on Wednesday to talk about it. I think he will agree to get recorded. I will double check. Send an email to remind him. Yeah. Okay. LZP is an important topic. I think in the future we might still read some papers relevant to it. I think we read several papers relevant to it already, but we might encounter more in the future. Okay. Have a good day, everyone. Bye-bye. Thank you, Natasha.